Okay, so this video is on Euler's method. We talked a little bit about slope fields last time. The general idea is that if we have some differential equation like 2x over y is dy dx is the derivative of a function, how can we think about what functions meet this condition, make this equation true? And as we saw last time, there are often infinitely many of these. And one way of envisioning what's happening is by looking at a slope field. So here's a Desmos slope field calculator. I will include the link. You can play around with this. You can put any function you want in here and see what the slope field looks like. And so we also sort of last time said that we can sort of just decide to draw the lines that go with the flow. And we're going to make that idea a little bit more rigorous with this thing called Euler's method. And so the general idea is that if you pick any starting point, so let's start, oh, I forgot to, one nice thing about this particular Desmos demo is that you can move a point around and see how the slope changes. So the slope's about 0 here, and then as you move it around, the slope rotates. So at any given point, it will find the slope. When it gets right on the x-axis, it disappears because we've got a 2x over y term. Dividing by 0 makes it freak out. Anyway, so Euler's method says that if you pick a starting point, and it's easiest to think about this on a slope field, but really just any starting point. Let's say it looks like I chose -5, 6. I could plug in -5, 6 into here, see that my slope should be what -10 over 6, which looks about right. And so Euler's method says that you start off with some points, and then you choose to go some fixed distance in the direction given by the slope. So if maybe we're going about this far, then our first section is just going to be a straight line that takes me to here. And then now that I'm here, I can look around. So the analogy is sort of you look for the new signpost. You figure out what the new slope is, and you go in that direction. And so the slope hasn't changed much. Maybe it's a little bit flatter now. So maybe I'm going more in this direction. And then again, I'm looking around. I say, all right, what is the slope at this particular point? This, I don't know, -2.5, positive 1 3/4. All right, so you plug that in, you see what the slope is, that tells you what direction to go in, and then you go this same fixed distance in that direction. So maybe this takes me to here. And then now I say, oh, hey, I've got a positive slope now. I'm going to be going this way. And you can repeat this process, and you end up doing what we sort of alluded to before, where you trace out some line that's going with the flow. And so there are pros and cons of doing this. The pros are, this is an actual technique that can be done. You can look at a certain point and say, what is the slope? And actually calculate where the next point should be. Unlike before when we said, all right, you just go with the flow, really we were just sort of sketching pictures that looked like they were about right. As a very calculusy idea, if we take the step interval and make it smaller and smaller, we're going to approach that smooth solution. So this is a way of drawing that, which really is what we were alluding to when we said that we're going to draw lines that go with the flow. The disadvantage of doing it with large step sizes is that you might be a little bit off. Notice how when we ended up crossing this x-axis, we were at this point, what was that, what I say, -2 something, positive 1 3/4. This took us at this negative slope crossing this axis, which we know that at this x-axis, the slope should be vertical, so it should have bent around a little bit sooner. So the actual function that goes through here is shaped a little bit differently than our Euler method, our Euler approximation of this system. So if we use a large step size, we can get sort of these slight errors this way. But again, just as sort of as a calculus idea, this is a way of defining what we mean by go with the flow, or what we mean by tracing out a curve in the slope field. What we're going to do is we're going to take these step sizes and make them really, really small.